Stoke's theorem part 2. Here's our basic statement of Stoke's theorem, which looks like our generalized Green's theorem, except for we call this three-dimensional surface S instead of R. S for surface instead of R for region. We have this surface bounded on the bottom by C. You can picture yourself as starting with a plane surface and like picking it up, stretching it, but it's bounded by its boundary right here. So we have the surface, we have the curve, and then there's nothing in the bottom. Well, if we take del cross F, sorry about that, I forgot that. If we take del cross F, this is the curl, dotted on N, and multiply that by dA. dA is a small little piece of area, this little window here. I took it over here and exploded the view. This del cross F, N is a normal vector, and then this curl sticking up here. It's not dependent on the surface, it's really dependent upon what the vector field is that we have. If you dot that, the curl on that, it'll give you the component of the curl in the direction of N. And if you multiply by dA, add it up, it says we get the same as this path integral. So this actually gives you the flux of the curl. If you can conceive of that, it turns out the flux of the curl is equal to the work integral around it, which if you think of this as a work integral, then this also has to give you work. This is area. This would be what would be called work density. And if you think of this as a fluid, if this represents fluid flow, you could call this circulation density. And sometimes that's used to describe what the curl actually represents. It represents circulation density. So we won't get too much farther into that. We're at the end of the semester, but if you're interested in what the curl represents, it gives you work density or circulation density. You take a little square, figure out the work around it, the path integral, how much work it takes to get around that, or how much work is done by this force, divide by the area dA, and that will give you a numerical value of the actual curl at that point. And of course, the direction of the curl is actually perpendicular to the plane of maximum circulation, if that makes any sense. Well, in any event, in this case, we're really interested in verifying Stoke's theorem, so you can learn what some of these symbols mean, so you're not intimidated by these symbols. This sort of vector analysis can be very intimidating. What we're going to do is evaluate this integral and evaluate this integral and show they're equal to the same thing. By picking this apart, it shows you what these symbols precisely mean. Here's a simple example. Suppose we have this cube and we have a path around the base. The surface is the upper cube. It's going to have 5 faces. This face, the back, the right, the left side, and the top, not including the bottom. It is bounded on the bottom by this square. I picked this vector field yi minus xj plus xk, and we want to verify Stoke's theorem. So we have to do a path integral, and then we have to figure out the curl dotted on N for each of these 5 surfaces. Integrate it. It's going to be 5 two-dimensional integrals, and hopefully we should get the same thing. We'll spend the remainder of this video doing this part, and then I'll take a break, and then we'll come back and have part 3 where we'll do this side over here. I don't want to do it all in one video. So let's look at f dot dr. F dot dr, obviously, we can write out a general statement for f dot dr, and then we're going to break it down into 4 different pieces. So So first of all, f dot dr is equal to yi minus xj plus xk dotted on, let me clear a little space here, dxi plus dyj. Okay. In 3D, ordinarily we would need a dz, but we're just traveling in the plane here, so that simplifies it a little bit. If this were some curve in space, then we would just add dzk. But I'm simplifying things here to keep it simple. So we have y dx minus x dy. That's what f dot dr is. I can put arrows on my vectors in case a physicist sneaks in here. So now what we need to do is evaluate that going around here. It looks an awful lot like what we did in Green's theorem. Well, that's because it is what we did in Green's theorem. And we can call this C1, C2, C3, C4. And so let's start with on C1. What's happening here is x is fixed. X is stuck at 1. Dx equals 0. And y goes from 0 to 1. Okay, so we can plug 0 in here, plug 1 in here, and you get f dot dr is equal to, put a 0 in here and put a 1 in here, negative dy. Now we want to integrate. Y is going to go from 0 to 1, goes in a forward fashion. So we can integrate 0 to 1, negative dy equals negative y from 0 to 1, and we get negative 1. Let's make a tally over here. Okay. Now let's move to C2. What's going on here? Y is fixed at 1, dy is 0. Oops. Yeah, almost got away from me. Okay, so you plug 1 in here and 0 in here. I'll just put these little numbers here. And guess what? We get f dot dr is equal to 1 dx. So we have to integrate dx. Now you have to be careful here. X is starting out at 1 and going back to 0. So we have to do this. And turns out we get negative 1. 0 minus 1. And then we can do C3, we're in the back side here. What's happening is x is 0, right? X is 0. Dy is 0. Okay, sorry about that, dx, my mistake. Y goes from 1 down to 0. Now, this is 0 and this is 0, so f dot dr is 0. So I'm just going to put a 0 right here. no sense in even setting up the integration. And on C4, we're coming along here. Y is okay, so we have a 0 here and a 0 here, so guess what? F.dr is 0. We're going to put a 0 here. Tally that up, we get -2. And so I guess we can make a final statement here. A line integral along C, F.dr, I forgot some of my arrows here, is equal to -1 plus -1 plus 0 plus 0, which is -2. Now, when we figure out the flux of the curl, which we'll do shortly, we should get -2. We're going to figure out the flux of the curl in the front face, the right side, the back, the left side, and the top, and it will add up to -2, guaranteed, because Stokes was correct. So we'll be back shortly.